Okay. Okay, let's start. Yeah. So maybe let's start by writing down the magical formula from last time. Which is in the end, what's interesting to me, and in the case of the moduli of quiver that we saw last time, we think of these phi's and c's. There's some kind of differential operators. The field coordinates is going to eat for you two of these differential operators, and we'll spit out a third differential operator. What's that differential operator? It's going to eat some symmetric Laurent polynomial. And I'm going to write this slightly different. Well, maybe let me write down what. Write it in a second. So you'll take your two differential operators. What are you going to do? You're going to take your symmetric Laurent polynomial, reinterpret it slightly as a sum of two individually symmetric Laurent polynomials. I'm going to keep track of z degree for one of these terms, and then you're going to something coming from the Euler. So that was the formula. But the more invariant way to write this inside like actual. So let me say the whole thing is supposed to live inside of X. And so K-homology, they eat things inside usual K theory of flexes of X and number. Slightly more invariantly, we can just write this inside the actual homology group. So becomes, so what is it? It says something like you.
Can I ask a question?
Yeah. Which light is this light?
Oh, I guess you symmetrized it anyway, right? But in principle, that experience has kind of different parities. It has different parities for two-fold and three-fold.
That's right.
Is the sign of that parity somehow anywhere important? You're going to get some kind of super vertex algebra or
I think the sign of that is kind of important
for what this group is. But, maybe here it only kind of comes into play in how many numerators versus like it only kind of comes into play in what this looks like. Okay. So yeah, I don't think it's super duper important. Okay. All right. So if we try to write this homology, it'd be something like we took the exterior product of B with C and kind of applied some kind of push forward with respect to some map, some kind of D of Z, where what's D of Z? D of Z applied to some functional is like precomposition. Something like that. Acting with first factor. And then this all backwards in time. I mean, maybe just write this and then we'll talk about it. First, we're going to cap with this thing. And push forward with respect to some now. So this is like the way you define each of the objects in turn. Z to degree box times 1. Yeah, sure. This is. I don't really want to write Z to the degree. I want to have some operator which represents post-composition. But yeah, sure, it's d of z box times 1. That's absolutely correct. Yeah. So anyways, my point is that there's some like this formula which I've been writing down up until now is the explicitly written, which is what this originally writes down in homology anyways. What's the point of doing this? Point of doing this. Now you can you can kind of ask on cohomology or on K-theory, have this thing on homology or K-homology, and you formally do everything. And what you'll get, operation, which is still a function of z. And this thing will eat one input, which now lives inside K cohomology. And it's going to spit out two things inside K perf. It's going to be exactly the categorical dual of this expression, which is not so different from what we originally had up there. It's going to take E. It's going to take pull back by some, Z degree 1. Then you're going to take 10. So for purely abstract reasons, this operation will satisfy the exact same thing as the vertex algebra, but all of those axioms will be dualized. Okay, so as an example, for vertex algebras, you used to have an axiom which, written multiplicatively, looks something like, if you want to know y of az b, then that's the same. A is that inverse with some action of your translation operator. Like one way to write the translation axiom or something like that. And so what are you going to get? Right? This is going to say something like you'll have some dual translation. There's still some actual operator. It eats something from your space and maps it into your space meromorphically in Z. And then you'll have some vertex co-operation y of Z inverse. And this is going to be equal to, along with some kind of operator. So here I've written down same kind of picture, which looks something like you ate A and B, and you have some vertex operation as a function of Z, and it spits out something. And on the other side, I've just read this picture in the opposite direction. And roughly speaking, the distinction between a vertex coalgebra and a vertex algebra is just kind of like the distinction between a coalgebra and an algebra. I mean, every coalgebra induces some algebra, but not vice versa. So and you kind of see the formulas already. Up there, you have some complicated expression involving some differential operator. Here, this is something very concrete. Right? This is just you take some symmetric polynomial, you multiply it by something, and you do some substitution of variables in like one factor. Right? You try to do process of moving from vertex algebra to vertex coalgebra, and you write this down additively, not much interesting happens. I think there's some statement you can write down that in the additive world, but multiplicatively, you have to be a little more careful. So maybe before we dive, so what's the motivation behind wanting to do this? the motivation that the cohomology of these kinds of stacks that we're thinking about X usually has some interesting structure. Okay, so usually this object will be some kind of Hall algebra, in the sense that there will be some notion of a stack of extensions corresponding to X. And using convolution with respect to that, you can write down some kind of product on this ring, well, on this group. Okay. And so it's kind of natural to ask the question if we have some structure on the homology of X, it's kind of natural to ask how this is going to interact with that.
You write the extension, that is very non-symmetric.
That is very non-symmetric.
There's really you extend one object.
That's right. Yeah.
So you're going to get a weight which is like half of the weight here. So
yes, that's exactly correct. Right.
Yeah. So this is there you find something more of like a like more of a quantum group. I mean, it's not exactly quantum group, but something.
It will be a quantum group in some setting.
Some slightly non-trivial group.
That's correct. Right.
But here you kind of took that object and you just symmetrized it more or less. Right?
I'm about to say something else. So Andre has seen 30 minutes into the future. So to happen is exactly what Andre said, that the Hall algebra structure relies on a stack of extensions, which is very much non-symmetric. And so the natural kind of comparison theorem that you will write down involves some version of this vertex algebra here, which is where the theta that we're going to use is not going to be a symmetric theta. It'll be some like 1/2 of the theta which we were writing. Theta is like some fully symmetrized. For this kind of comparison to go through with the Hall algebra, it's forced upon you that you take 1/2 of that. You take something truly non-symmetric. The axiom will have to change. So will have to become something non-trivial. Right now, I've just written something super naive, which is you literally take this unbraided notion of usual vertex algebra and you just write down the dual, right? But equally well, you can introduce some. It's called a braided vertex algebra. There's also some notion of that too. But here the correct comparison theorem. Vertex algebra. And that will be compatible in some way, which I'm about to state with the Hall algebra itself. So that's the motivation for why we want to make everything dual. It becomes much easier to write down the comparison.
Can I ask a naive question? So can you remind me how's the theta z defined?
Yeah, sure. Yeah. Okay, so theta z is gonna be something like the Euler class. Okay, so if you're working in the usual Euler class, if you're working in K theory, it's the exterior algebra. It'll be the Euler. The normal bundle of what? Got your X, and your moduli space X has many components indexed by alpha. And so the component X alpha plus beta is going to be like X alpha times X beta, and then map into here via sum. And so that locus has a normal bundle, which if say X is the moduli of coherent sheaves or quiver representations, look basically like so e.g. what's this normal bundle? It'll look something like X of universal bundle over alpha, universal bundle over beta, plus universal bundle over alpha, something like that. So this is like some very great gems. And for quivers, it's super easy to write this down, which is yeah. So here, Conveniently, I just erased this. So in the vertex algebra world, you eat something in class alpha, you eat something else in class beta, and you produce something of class alpha plus beta. In the vertex coalgebra world, you eat something of class alpha, and you produce something in class alpha 1 and something in class alpha 2, ranging over all alpha 1, alpha 2, adding up to alpha. So it's usually helpful to write down the components of that as something like this. So then here you'll get the sum map alpha 1, alpha 2, and here you'll get.
Okay, got it. Thank you.
Okay. Oh, you're really using your phone. Nice. Okay. Right. Okay. So let's see. All right. So now I want to try to convince you maybe having some kind of the trivial swapping operator is forced to you pass from additive things to multiplicative things. And that comes kind of being a little careful about where these objects kind of live. And in particular, what their specific dependence on Z is. Right? So past for additive vertex algebras, which is going to look exactly the same, but Z inverse will be written additively, so it'll be a minus Z. Right? And if on the left-hand side you have the one which takes state space series, on the right-hand side you have some other operation, and it takes place in your state space series in minus Z. And of course, these rings are equal, right? So it's additive. And multiplicatively, you're going to have to start being a little careful because now you have this 1 minus Z. And over here, you're going to get Z inverse. And this is still the same up to multiplication by Z anyway. Multiplicative. But now, when you pass to the coalgebra, so what does it do? It eats something in your state space. It produces two things. And the dependence in Z, I claim, should be something in inverse, opposite direction that we usually. Okay. And the reason for this, you can kind of see it from the formula. Previously, for the what did we have to do? We had to take. So we had to take theta. And what does theta look like? Theta is, speaking, some product of some fractions, and the fractions look like maybe you have something in the numerator, which we don't really care about. That's always going to be a polynomial in Z. Then you'll have some kind of denominators which maybe look like 1 minus Z times the line number. Maybe the Z has some power, but let's not deal with that. And then what are we going to have to do for a vertex algebra? We have to expand this as a series around Z is equal to 1. Right? And so we're going to have some expansion, like 1 minus Z, some power. There's something up here, 1 L. Something like that. What happened for vertex algebras is our finiteness axiom for the inputs that we have is going to truncate the sum at some finite negative order. That was the point of having this finiteness axiom, where we said that the functionals we want to think about are going to vanish for high enough powers of the augmentation ideal. But now we have this vertex coalgebra, and we're not hitting it with any functions. We're really just eating some sheaf and producing two other sheaves. And so now there's no good reason for this to truncate. And in fact, there's good reasons why we shouldn't truncate it. And so what's happened if your vertex coalgebra take values in meromorphic series in the inverse of your previous variable. So because I'm going to write a bit more. So it turns out it makes sense of be a little careful because that z to the degree 1 operator still take value somewhere. So I do is to do something like this. And this is not going to be the same as just series. You just do the usual change of variables. Yeah, so yeah, but if you do that kind of completion, so if you expand z inverse 1, you're going to get bi-direct series. And for vertex out.
Whatever. At three interesting points, 0, 1, and infinity. Can you just say which function you're going to take?
No, I think my point is that I have a stable meromorphic function. I have some essential singularities. Yeah, it'll just be some series with.
But that's.
What do you mean? I mean, if I have some series like this, how are you going to replace it? Sorry, not following. Mm-hmm. I mean, if you expand this as a series in 1 over z.
Yeah. So I'm just saying.
Yeah. So are you saying? Are you saying that you want to replace? Is that what you're saying?
Well, that's certainly where all these things lie.
This thing is equal to 1, right?
And that's also the same here. So I'm just saying if it's like with the Yankees, has a translation thing. The Yankees is about, like yours in the Yankees is about expansion in one over like U. And then the Yankees, you have translation automorphism, where you take U plus something, and every series in 1 over U, you can re-expand in series in 1 U plus something.
Yeah, I think this is true. For me, maybe it's just a little conceptually easier to write it like it's. You kind of you see that the operator z to the degree takes some values in here, and the term takes some values. Yeah, I guess if you want, it's fine too.
And can we just ask the equals here?
So here we're now thinking of the dual K-homology, which
Really just is the original K group. So these inputs really are just some sheaves, some coherent sheaves on the original stack. So
But this to me looks much better because this looks like a normal expansion.
yeah, right. So
One kind of moral that I want to make in part is that it's much easier
to work with this object than it is to work with the original non-upside down one. Yeah. So I think
We're actually scattering. Which of these guys are framed? Most, just like I talked, is one of them framed?
no, there's no framing here. So we
Oh, then
we
there's
started
no
off.
framing at all.
Yeah, there's no framing at all. We started off with some category of objects that we want to consider, and we formed some moduli set, and that state space really is the K group of that moduli set. So previously we had some more complicated setup where we had to take some K-homology group, which has some complicated axioms. But here I'm saying you can look at the categorically dual picture, which is just like the usual K group of that set, maybe with the word perf here. So the K group of all perfect complexes, which for most intents and purposes, you can just imagine this is the K group of vector bundles.
So this is somewhat going to make sense even on the smaller objects without switching up to the first level of adding this one vector.
Yeah, but previously that's not making sense too. I mean, previously, so this is like some cohomology theory, and previously we had some homology theory. Yeah. So if you just want to work with a vertex algebra without any reference to wall crossing, that vertex algebra is really something like kind of intrinsically associated to the stack. Right, so previously we had some vertex algebra structure on here, and the point that I want to make is that then purely formally on the categorically opposite side of the picture, you're going to have some vertex coalgebra, something like that, and that's really like some purely formal kind of statement that really requires no additional proof. And the moral that I want to impart is that, at least for our geometric construction, maybe it's easier to study this guy than to study this guy, because this guy is just you eat some sheaf and you do some operations to your sheaf, whereas for this guy it's you eat some differential operators which act on sheaves, and you do something to the sheaf that is reflected in like what you do to these differential operators. That's slightly more complicated. Okay.
So,
yeah.
So when you have that V plus the first thing is that V can be only non-zero, and then the second thing is that V is like far away from one.
Maybe if you want to think about it analytically, it might be better to do it. So you have some coordinate Z inverse, and you're just thinking about some kind of meromorphic function Z inverse. Yeah. Anyways, right. So regardless of what you call this side, when we look at that, at some point you're going to have the right-hand side, which is going to be some series in Z. Yeah. So already, even in the multiplicative case, if you don't want some braiding, like if you want some concept of unbraided, multiplicative vertex algebra, you don't have this. It's forced on you the moment you write down some axiom like this to have some trivial braiding operator. So actually, when I wrote this statement down, right? Because you can never put some kind of trivial braiding operator here, otherwise, in the right. So actually, well, okay, so maybe let me leave this in quotes, right? There is And what you actually should have is some non-trivial braiding. Yeah. Now, when I say the word vertex algebra with no other. Yeah. So you're going to need some non-trivial braiding operator as check, which moves you from, say, series in Z inverse to series in Z. And you get some kind of axiom like this instead. So this is the right thing to write down. This is the wrong thing to write down. The wrong thing to write down because it doesn't make sense. So that's one kind of new subtlety that you see in this kind of theory. And this kind of subtlety is also reflected. So okay, maybe let me give you another source for this kind of subtlety, which is multiplicative. There are many different ways to expand rational functions of two variables. So note this is going to be some, yeah, if you want to be extra fancy, that's how you say it. Yeah, that's right. But
If you have where the mononomial is like a two different equation, what does it say?
right. Yes, Andre. Yeah. I totally agree with this. I'm just laughing because I was about to write down some very much simpler algebra facts that illustrates exactly this. So say we have some rational function jointly in Z and W, and this is multiplicative analog of something 1 over Z minus W, right? But if you take 1 over Z minus W and you say I want to expand it meromorphically in Z or meromorphically in W, that expansion is unique. But here you have a choice. Even in the non-equivariant setting. Okay? So nothing that I'm going to say today is going to be equivariant for simplicity. Okay? But even in the non-equivariant setting, you have a choice for how to do this expansion. Because, for example, what's this going to be? Can multiply everything by W minus Z, right? And then you can choose to expand this meromorphically in 1 minus Z or meromorphically in 1 minus W, following with the usual kind of prescription. But equally well, I can do something kind of funny. I can multiply everything by Z inverse, and I'll get Z inverse minus W inverse. And now I can expand meromorphically in 1 minus W inverse, or I can expand meromorphically in 1 minus Z inverse. And these are truly different expansions, because here, 1 is special in the same sense that 0 was special in the original additive setting. It's the identity of the group.
Like Paul field theorem, plane, the cylinder.
Yeah.
The cylinder is playing with two separate points. So
That's correct.
there's,
But it has a third special point. It has the special point 0 and infinity, and it also has a special point 1. Yeah. So that 1 is special for the same reason that 0 was special originally. Yeah. So in the additive world, you want to do every expansion around 0. In the multiplicative world, you want to do every expansion around 1. Okay. So here we have something written in the multiplicative world, and we're going to want to expand around these variables being close to 1. And so here you'll get special in what? These? No.
Oh.
Yeah.
nothing. One is just the same as every other one. I think your theory is an extra structure. There's something special at one. Maybe there's extra framing knowledge you're putting there. There's some structure that makes one special. What about nothing?
I suppose what you're saying is true in principle. I mean, you can replace this 1 with a 3 if you want.
Yeah.
But you can equally well scale your variables so that goes back to 1. I think maybe from the perspective of some object living over the cylinder, sure, there's nothing special about 1, but there is something special about not being 0 or infinity. Yeah. So here I choose the right one because 1 is the exponential of 0, and that's how you pass. Yeah, that'll make your life much easier. Yeah.
There are two different expansions.
Right. Okay. Okay. Yes. So let's try to finish this exercise in complex analysis. Okay. So let's write down this expansion. Let's gonna matrix series in 1 over W over 1 over Z. No, 1 minus W over 1 minus Z. Right. That has some radius of convergence. It converges whenever this thing is less than this thing. Right. And also write this down. This has some radius of convergence. It converges whenever this thing is less than this thing.
That's the second step.
Yeah. So the point that I'm trying to make here is that usually when you do additive vertex algebras, right, what kind of axioms are you going to write down? You're going to say, like, maybe I have some kind of locality principle, right? That says, okay, I have some vertex operator y and z. I mean u and v. So u and v for me are additive variables. Okay. So you'll have things like locality axioms that says this is equal to the opposite thing, right? Something like this, right? But what does this mean? This is some meromorphic series in V. This is a meromorphic series in W, in U. So the left-hand side is valued in series like this. Right. The right-hand side is valued in the opposite thing. How are you going to compare this? Right. So the it's better to say something stronger, which is that actually these two we require that they're actually the rational the series expansion of the same rational function, which has poles along the diagonal in U and V. So it's yeah, that's right. Yeah, but since here I'm saying something about expansions of whatever, I want to phrase it in that language too. So you imagine you have some rational function, 1 over u minus v, right? It has some expansion that it lands in here, also has some other series expansion that lands in here. And this kind of equality says this is equal to this if it actually comes from some rational function. Right. So now I'm saying that in the multiplicative setting, you still need some concept of expansion. Right? You have some jointly rational function of z and w like this, which is completely analogous to this. And you have to have a notion of how do you expand it and how do you expand it so that it lands here. And I'm saying that while you had no choice in the additive setting of how this expansion works, you do have a choice here.
Why not the same choice? Our typing case, we are choice about who's closer to 0. Up there, you have the choice who's closer to 1.
Sorry. That's a separate kind of choice. So that choice that you're referring to is, do you expand it or do you expand it here? Now I'm saying the notion of expansion itself is not unique. You can expand it in 1 minus w and 1 minus z, but you can equally well expand it in 1 minus z inverse and 1 minus w inverse. The choice you're talking about is, do you expand it when this is bigger than this or when this is bigger than this? That's a separate choice.
1 minus w inverse.
Mm-hmm. I agree. Yes. But so maybe let me write what I was about to write. I mean, once you expand, this is going to be some series which maybe looks like this with some stuff, right? Which looks like this. maybe with some stuff,
Yes.
right? And these are regions look like. I mean, it's like, what's it gonna look like? No. Right. It's like saying in series. Like, I don't know, you like is greater than 3 because there's some other series. U to the minus k plus 1. K is greater than or equal to 0 or something. These are expansions of the same rational function, but they're not the same series. They live in 2 different rings.
What was the expression?
Mm-hmm. Mm-hmm. That's what I'm saying. Okay. Yeah. So actually thought that it looks something like.
Yeah.
And right, exactly. So whether or not these two get some in around 1, that I completely agree with it. And the way to see that, the way to maybe state that alternately is that in some neighborhood around 1, you're free to rewrite things like W inverse is equal to some. Okay, so anyways, that's indication that you're going to have to deal with problems like what happened, where having some series in Z is really very different from having some series in Z inverse. So these are two kinds of sources of the exact same problem. But in fact, for vertex coalgebras, it's kind of any more questions about this? Is it okay? Yeah. Oh yeah, sure. That I didn't finish drawing this slide. I mean, what so imagine that just plot what these regions are. One looks and the other is a bit more complicated. It kind of looks like this. I wish I had multiple colors. Yeah, I mean, you can just plot what the regions of convergence are, and you see that they're neither disjoints nor are they the same. They will agree inside some small circle here, yeah, which is a reflection of what Peng just said. One over U. If you put these expressions additively, here you're going to get something like U over V to the K. Over here, you're going to get something like V over U to the K. And these two regions are complementary to each other. Yeah, but here I'm making the statement that these two either complement or they really are two separate choices. Okay, so maybe now let me state the compatibility theorem. So first, like I said, yeah.
This double check is possible here.
asterisk. Uh-huh.
Easy and
Yep. So it's this U in the categorically blue, which just means what used to be inputs are now outputs. What used to be outputs are now inputs. Right? And then I realized that in the multiplicative setting, there's a lie. You can't have something trivial like this here because this object and this object live in two different rings. So it's to have some spreading operator is in the geometric setup in one second. But yeah, that's one way to say it. Yeah. Sorry, not parallel transport. It's more just like how to like re-expand solutions around zero into solutions around infinity. Okay. 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 I haven't said what this is in a geometric setup. And in fact, now I will say what it is in our geometric setup. Yeah. So let me actually just erase this bit. Maybe leave this in place. All right. So like Andrea observed earlier, if we want to compare this object with a Hall algebra, we want something non-symmetric here. And so what we're going to do is actually when you try to check a formula like this really gives you a vertex algebra, you really don't need that many things. You don't really need that many properties from this data. You just need some compatibility of this data, the degree operator, and the sum map. Right? And that, roughly speaking, just translates to the fact that its theta is some Euler class of something which is bilinear. But if you think of these axes, each of these axes individually, there was no like real need to have some symmetrized version of this. If we just care about the fact that we want to form a vertex algebra. So the object we want to consider now is just going to be 1/2. In the formulas from before, I needed the symmetrized version to get some kind of unbraided vertex algebra.
No, I mean, for the whole problem.
Oh, for the wall crossing. For the wall crossing, yeah, you really need the yeah. Yeah, I don't know. I think it maybe kind of depends on what relation you're looking for. I mean, there's the stupid end. The relation has just chopped off half of this. Mm-hmm. Oh, there's no identification of this vertex algebra. What do you mean? Vertex algebras, they're kind of identifiable.
So we're talking about another shape from like on triple,
Mhm.
shape of vertices.
Mm-hmm.
No, that's some kind of continuity with the zero.
That's not so clear to me.
Isn't this just going to be just like a topology?
This is, well, that's not clear. I don't know. Yeah, it's some kind of vertex coproduct. I don't know if if some piece of it, maybe like if you take some residues in Z or something, maybe it's equal to the shuffle algebra coproduct. To be seen. So for theta, we're going to take the some sense like some kind of kernel which will match up with the kernel for the shuffle. So when you plug this into some formulas, you'll see that the non-trivial braiding operator kind of just looks like you take theta alpha comma beta of Z over theta comma alpha of Z, and you do some kind of expansion. Yeah. So I mean, imagine theta has a term like this. That was no person. So like imagine when you run equivariant localization, you get some terms in the denominator, and it's important that these terms come from moving terms inside your term. So maybe an object like this kind of doesn't super well defined. I mean, it's not that because it's fine, but you're not guaranteed it's well defined. That's the only reason I don't write this Z over here. Formally speaking, yeah, that's true. So formally speaking, it's true that if you hit theta of W with Z to the degree, it's going to be equal to theta W or something like that. We just avoid exactly what you just said because theta 1 is not so well defined. Okay. So in the geometric setup, you have some braiding operator which looks rough. And so in particular, in previous and in the world vertex coalgebras. Yeah, so even in this case, when if you have some theta which is symmetric in alpha and beta, you still get some non-trivial braiding operator for the vertex coalgebra. I mean, it's kind of like a, I don't know how to say. Yeah, that's correct. Yeah, that's right. Maybe up to some H bar factors or something. So now some braided vertex coalgebra on K theory of X. So this has some braided co-vertex algebra structure. And so now we can finally write down the compatibility theorem. So theorem so let's abbreviate this as our state space V. So start from V tensor V, you can do two things. You can either apply your V, or you can do your vertex coproduct. Here you're going to do vertex coproduct, box times vertex coproduct. Here you're going to get V tensor V. Let's Here you're going to get V4 with some more stuff. And do all that it's saying is that one operator is a homomorphism for the other. And there's a small subtlety here because your vertex algebra is braided. Sorry, your vertex co-algebra is braided. And so somewhere inside this diagram, you're going to have a braiding. We're just going to put that here in the, I guess, the second and third tensor factors. Is that this whole thing comes. So why is this interesting? I think even if you don't care so much about Hall algebras, so sorry, I think this is still a conjecture by Casero, Arnolo, something like this. In the K-theoretic setup, I think originally in cohomology, this maybe was due to Ben Davison. Some kind of statements like if you take what's called the pre-projective stack, so the X, where X here is a quiver representation. So the cotangent bundle of the stack, if is like T star V mod G, and the cotangent of X is going to be the zero locus of the moment map mod G. So as you start off from some quiver, form this K group, and here it doesn't really matter if sorry, yeah. Let me just write this. Some conjecture to that is supposed of some quantum group. Want some positive part of positive. Okay. And I think this is proof for something like finite, right? Do a finite ADE type maybe, and maybe also of affine ADE. I don't remember. There's some conjecture to this effect. So we can X is the moduli space of quiver. This is called the pre-predict moduli of projective algebra associated to also unframed. Yeah. Yeah. Okay. So in particular, this kind of compatibility says something about some compatibility of the vertex vertex co-algebra with some kind of quantity in this kind of specific application. Okay. Is true in even more generality. So now maybe let me try to see how generalized. I should maybe say at this point that the concept of like having the ability of a vertex algebra with some co-algebra in the exact sense is kind of like not a, this is what people call a vertex bi-algebra for obvious reasons. algebra with a coalgebra, you get a bialgebra. If you pair a vertex algebra with some coalgebra, you get some notion of vertex bialgebra. But it's kind of curious to me that there's no like exploration of what happens when you pair a vertex algebra with a vertex coalgebra. Kind of unclear what goes on there. Maybe there's some obvious convergence issue or something that make this nonsensical. But as far as I know, there's only on one have some vertex algebra, on the other maybe you have a co-vertex algebra, and on the other side you have an algebra, and you pair these and you X by it. And so one way to state this theorem up here is that V, there is the structure of a vertex bialgebra. Multiplicative vertex bialgebra. Okay.
I think you mean you want to add one key.
Really? Maybe I'm misstating their conjecture. That's right. That's actually
You have, imagine you have.
Uh-huh. Uh-huh.
And then of course we can have half of that. And then, and then you can have and then that's half of that function.
Is it not the generally written it here?
No, this is sort of thing for genetic things, right?
No. I think their conjecture is really like
Your modular quiver representation.
okay.
Q doesn't have to be
Q doesn't have to be.
ADE.
Oh, right. But this has to be an algebra that has some kind of genetic realization. If I take, I don't know, E8 or something like that, that's it, there's no, or no, maybe E8 does, but we have F4. They give you like whatever F4 or some algebra like that. I mean, this is the many more Lie algebras, which don't necessarily realize the quiver.
Like,
Yes.
right.
Right, so I just give you some metric, whatever. I mean, I got it from somewhere. And then I make that construction, I can also make your construction.
That's correct. Yeah.
And then it's the question of compatibility of the two structures. Is that actually relies on some geometric input, or it's?
Yeah, that's a good question. I'm hesitant to say anything outside of the geometric picture.
But where do you actually use it?
Maybe there's some remnants of geometry hiding the fact that this braiding operator with the formula for the vertex coproduct, which I've written, you still have to show that this forms a vertex coalgebra. So in particular, that means you have some compatibility of the sum map and some notion of the degree operator. The degree maybe.
There's some kind of loop rotation.
Right.
The degrees come from loop rotation.
Yeah, I'm not so worried about the degree operator actually. Maybe like the actual remnants of geometry come from some map. It's maybe not.
But I think it's a question of if I ask for just the diagonal matrix element of the R matrix, what do they look like? And then I think this has to do. There's some. Since people study that question, because this is a question about how the Cartan torus acts in representation, and there's some abstract stuff.
Yeah, there's
about
some
description of what this
That's
yeah, that's why the name of this whatever Q-cat, not before the Q-cat. It's just Q-cat. The Q-cat tells us what this matrix elements look like.
Yeah, that's right. Yeah,
I suppose that's correct, right?
maybe you can just get rid of all the geometry here. Really just say something about the algebraic properties of those weights, and once you have some appropriate property of those weights, maybe fine. And then yeah, I think the question you're asking is a very meaningful one. Yeah. Not something I've looked into, but would be interesting. So maybe what I can say in that kind of direction is that the proof of compatibility again is very formal. You really just draw out what this diagram means, make sure every little square commutes with something. So it's certainly true that there's not much actual geometric input which goes into that proof. So I'm inclined to believe that you can just reformulate everything as facts about maybe like the form of these rational functions or something to do with the R matrix. So I'm inclined to believe that this kind of compatibility will hold more generally outside of the geometric sense, but that's work to be done.
Okay. That's understood by the fact that one day maybe already has produced some sort of genetic relation as O, as P, and other.
Yeah, I don't know about that.
Yeah, but
That
I
would
think
work.
it would, I know, it's a big difference.
For me,
Once you cover in AE, there's so much stuff. But no, but if you take that. No, I guess if you take quiver with arbitrary, there's something for arbitrary things.
I'm only aware of GL and orthosymplectic. Rest of the world and yeah. Right. So the last thing I want to say for today and also for this whole series of lectures.
But then maybe to stress my
Yeah.
mistake, so I'll just put my mistake.
Mhm.
This side of morphism says whatever. Anything's written on the board says nothing about the actual wall crossing formula.
No.
None of this has anything to like actually do with wall crossing. It's really just it doesn't know anything about the wall crossing. But yeah. The wall crossing business was where all this was born, but somehow if you just want to study these kinds of objects, you don't have to do anything about wall crossing is like some complicated usage of these objects. Right. That's right.
Then you took the perfect help, and you in some sense extracted the top of it in the top of the factors.
Yeah, that's right.
And then you got something else that you were the quantum group.
That's right.
So then the question is the original Libra.
Yeah, but here
Practical.
no, I don't think I don't think this is going to be once you pass the residues. So
It's not unthinkable that the original bilinear operation would have some kind of expression.
oh yeah, it's not unthinkable. But for me, it's also not thinkable.
Okay.
Yeah. So at face value, what I can say is that if you just hit this thing with the residue map, like you hit this like half of the original vertex operation with the residue map, that's not going to give you a Lie bracket. But maybe there's something more sophisticated you can do. I don't know. In principle, yeah, like all the data is encoded in there somehow. You just have to do something.
Or else you can put that. I mean, that's like I've been asking for operator forever. That's often fine. One part of your system is structure, and the other part is
That's some kind of insertion. Mhm.
The
Yeah.
that operator of the
Possible. So Yeah, there may be,
There's some imagination.
because off the top of my head, I'm not sure what it means to have some like vertex operation with insertion.
Yeah, but in this is something, you have some kind of, you have some, whatever, you have upside down wall, which you can then follow with some algorithm.
Sorry, so here
You have your original
at this
upside down.
vertex of the y, right? It's eating something, and something will happen to this object that it eats, and then it'll get capped with this theta.
Right,
of the
let's
beta.
have two different fields. There's like half theta.
Yeah, right. And you'd like to change this picture into this picture. Theta alpha beta z tensor theta beta alpha.
Yeah, that's what I'm saying. That this is can accomplished by saying that I applied some operator after I fork.
After you fork. Oh, I was thinking maybe before you fork. But I think yeah, that's absolutely correct. Here you can put some operator, which is multiplication by this.
Right.
Yeah, that's totally correct.
Well, but in fact, I mean, in fact, it comes to the effective. Some kind of joint. Yeah. And so if you have some understanding of that operator.
Yeah, but understanding that operator is as you know very well, hard.
It's not easy, but it tells you something. It tells you that you have that operator, you stick it in.
That's true. Yeah, that's correct. I think there's a big world of questions like that that are waiting to be explored. Like I think for any kind of
Interesting operator you might see in this one.
you can kind of ask
How will that operator interact with this
extra vertex coalgebra structure, and special case of that question is
Right.
yeah, and I think that's a whole world of questions. I haven't begun exploring any of it. Everyone else is welcome to.
But if you have to think like a boundary asks you, how this can be applied in real life, you can tell me. I just need to think like if this operation does the way force.
I think that's but maybe
Okay.
yeah, right. Yeah, so I completely agree. This is a very meaningful question to ask, and I have nothing to say about it. Yeah. Okay. Any other questions? So let me just wrap up with a very general kind of remark, which is that inside this y, right, this y had three pieces. It has that. And it has the operation that you take the tensor product by something theta. And so, like, can you make sense of this? In some context more general than K perf of X? And the answer is, there are lots of other K theories where you have arbitrary pullbacks. For instance, you can take what's called the critical K theory of some space X with some superpotential W. And roughly, what is this object? There are models of maybe a kind of let's just say, let's say it like this. Let's say you take the usual K group, zero locus of your superpotential W, modulo K group of perfect complex of zero locus of your superpotential W. Okay. So, of course, if this space zero locus of W was there's no discrepancy between K and K perf, and this thing is trivial. This thing. So most people here are probably. Well, anyways, you can take the usual singularity category, pass the K, get something critical K theory. And critical K theory equally well has a realization as the K group of matrix factorizations on the ambient space X with superpotential W. Okay. So in particular, if your ambient actually, I think this equality holds when the ambient space is smooth. So usually when you think about these critical K theories, matrix factorizations, and so on, you always think of we'll assume that is some actual vector space. What's some super? What's matrix factorizations? It's you have some two periodic, or like almost two periodic complexes on your ambient space X. And for a smooth ambient space, it doesn't really matter if you ask for complexes of sheet, complexes of vector bundles, they're all the same. So the point of this whole discussion is that inside critical K theory of some smooth ambient thing, you have arbitrary pullbacks. And in any kind of K theory where you have arbitrary pullbacks, you can start asking, will this kind of expression make sense? And in critical K theory, the answer is yes, this whole expression makes sense. Modulo some technicalities about whether or not you have a Kuhn theorem. So I mean, a priori, the outputs the K group of maybe, let's say, like X alpha times X beta as the K group alpha tensor product K group of X beta. And it'll be even more not the same once you include some equivariants. So
Okay, like every time people do
yeah, it's usually okay. It's big. That's right. That's right. But I'm just pointing out that maybe this is something you have to. But anyways, so modulo mild technical considerations like this, these kinds of vertex coproducts will make sense inside critical K theory. And you can start asking, will diagrams like this still hold for critical K theory? Because, for instance, if X is some moduli quiver representations, there is some notion of a critical Hall algebra, where you write down the same kind of X stack and you do the same kind of push and pull from it inside critical K theory. So, if I'm not mistaken, I think this was just recently written down by Tudor. Tudor, whose last name I can't really pronounce. Tudor Paduraru. My apologies to Tudor. She's watching this at some point in the future. Right. So then there the in this kind of setting. So here is that actually we cool. And you'll have the same kind of compatibility for almost exactly the same reason. The super formal proofs. Everything really carries through. And this should not really be surprising, because in some sense, like the ordinary K groups you can sometimes think of as really just special cases of these critical K groups. So the last thing, right? Sure, that small remark. There exists what's called dimensional reduction theorems of the sort that, for example, if you want to realize K let's call it X sub Q. Sorry. T star of this this is going to be equal to, even equivariantly, the critical K group of quiver moduli for some triple quiver with some special kind of triple superpotential, which looks like the pairing of your ball with some extra coordinates along your gauge group or something, along the algebra of your gauge group. So this slight generalization for critical K groups in general, that assumes the original form in the case of things quiver moduli or other things that admit some kind of critical K theoretic description. Okay, that's all I have to say about anything relating to the subject. And thanks everyone for all your attention these past few days.
Imagine we have this defined for some kind of correct stuff. You'd be able to do quasi-substitutive crossing.
Oh. Why would you have to pass the derived steps for this? I mean, you can equally well write this for the ordinaries.
Oh, okay. I thought you said if you know to do the entire.
Right. Yes, of course. Right. Yeah, that's right. Yeah, those kind of wall crossings. I mean, so we can even take a step back from that. We can just ask for like, will this kind of wall crossing give you any input into things like DTPT? Right. That's like kind of
like a minimal of the growth.
Sure. Yeah. Anyways, I think maybe what I want to say is that in those kinds of wall crossings, you have to worry about what destabilizes and what root stabilizes. These things which will destabilize, which will kind of look like sheaves. And I'm told with what should be the on these kinds of moduli spaces, and full obstruction is. I'm told
You frame them, you take point shapes, you take.
Yeah, but so somehow, what's the way to put it? These semi-stable invariants, they have to come from somewhere. Like you need some original source of virtual classes, either framed, either not framed, or so on. And I told something about like the moduli spaces of these point sheaves having some kind of virtual classes which are not so well framed. Yeah, so well, that's something can be done there, but I've been told there are some difficulties.
You know what to do for quiver with no loops and no potential. Is that
So for quivers, I can write down the vertex algebra for literally any quiver and any kind of super. Modulo maybe IO technical.
But this is the thing that you just change the definition.
Yeah, right.
and the z function? That's also something that's known explicitly. There was one in the first and second talks.
The z. My right, that z was supposed to be like some homological analog of the virtual cycle. Yeah. Those are maybe not super explicitly, but they do exist, and we can get some handle on them. So I mean, they're implicitly defined using this formula. So,
I think from string theory, you really do see the Riemann circles where these things live.
okay.
And the Riemann circles, because of the stuff you put there, really has like 3 corners.
Uh-huh.
And the 3 terms in your formula are just the standard stuff in the CFG, a word identity of the CFG, which says that, you know, you can move from here to here to here. And it's just the 3 terms.
Sorry, which 3 terms am I?
Well, it's
which
3
ones?
terms at the beginning of your first lecture. Well, one of the terms is more complicated, it's just like, I guess.
Ah, you mean the,
It's just very vaguely, but. It's not one out of 12 business.
What you're talking about last time, like A, B, and C.
right, that's right, that's right.
So I think this outside, is one. The other.
Uh-huh.
What has, the stability does matter, like change as you move this guy around. What you set a stable object is also changing. So there's some really pretty stories. You said saying it sharply. And you just come
I'm not so sure, but okay.
Yeah, right. No, yeah, especially from what we're actually just now talking about. I'm sure that we could probably spell it out in principle. If we follow.
That's
Okay.
the thing what to do. Not do. Frame 53 and put these 2 frames on one of them. That's something. The point that we should first understand is that that's how you know.
This is not what we usually say. This is the difference between having this to have something centralized and the usual something.
It's not so you only non-compact object using the V guy. There's a total non-compact. Everything fits in the same. Right? It's still. In the same way you can fit all the. Well. That's all this negative stuff is roughly a 1/4 of some people. So one.
I don't know, I can say, so maybe we can have some kind of.
This is not a course.
Some kind of discussion in which there's several threads of this discussion. One thread is, I'd be curious, I would be curious to know, what that, in the world of threefold, like if there's, that in the world of threefold, there's not just the quantum, it's going to be some project, kind of looks like a quantum group, but has more, and I was, I was curious about how whole algebra is to read, and what the quantum group is to read, and I'm somehow curious to see what sort of stronger structure was involved with different. But that's kind of one, which is people experience to think and do it. That's something we still to go to work on. I really think so. Not sure how exactly. But that's the X operator, even for certain.
For all that, you need some like actual. Not, I mean, it's sure that data, but not what actual nice. In person, not just like we want we're not gonna coherent data. Well, yeah, but you don't want to grade here. You don't want to that. You want to grade something. You want to grade.
So the other thread of the discussion would be you or Spencer or you together with Spencer somehow explaining the language in which you speak to other people. This was the best based on this star, which is in every single one of people you wrote in the past.
The same, but the same.
So I agree with that. So but that's for
Yeah, I'd like to second this amendment.
But in the story, if that's the point, it's variable to scale the volume form of the sequel is or is not turned on. It's not.
It's convenient to have it. It's very similar to the end, and it's works particularly nicely if you respect that. I mean, somehow this the thing that if you want to compute the rest of the infinity, it's good to have that. There.
Good, but is it there? What did you call it?
Can you call it
T, something like that. Yeah.
T.
right?
You can call it whatever you want.
Yes.
So for me, at some point, I T is like a log of h bar. That's right.
But you know,
It is, of course, it's not an ordinary kind of algebra because you get this funny poles shifted by.
but you don't get it. It's not a Q or a T off.
Sorry.
Like
The
1 to 2 to 3 to 4. Not to see.
That's the structure that you have, so it makes sense. One would have to explain why.
I don't know, it's not. It sounds that you have to delay it a little bit. So to speak, you have them.
yeah, you kind of have them scattered all over the place along your torus. Yes.
But there's still somehow, for any two options, somehow still find to me.
Once you fix any two inputs, yeah, there's finitely many singularities which will vary as those inputs vary.
Yeah, but it's not like you get some kind of, some kind of trains of poles.
No, you don't get some like one dimension or higher dimensional. Yeah, it's really just some collection of points. But where those points are on your torus really are going to vary as functions of your input.
It's always some kind of like a nuclear situation.
Yeah.
Then we have poles not just about the centers of wherever each core overlaps with each core. So that's,
Is there some precise statement as to the location of the pole?
yeah, of course.
Yeah, it'll be the weights of
The pole can be shifted by all possible differences of constants involved. It's like imagine your kind of object.
I mean, maybe we can be super in the case of the quiver. Right? Yeah. So I mean, yesterday. Anyways, last time this Y looks like in the case of the quiver with one node, no arrows, right? But, yeah. This what's it called, like X of your so here you're going to have these, right? And you can ask, what is X universal going to be? And this will have some kind of expression like you're going to be over all your vertices. Maybe V is like the I over all your vertices I. So here. So I mean, you should keep this in, but I'll write something which works for all quivers. Okay. Over something like hom vi. Sorry. The moduli space of these things will have X by the dimensions for these V's, right? So we think about V alpha and V beta. Right? And so what's this going to be? This is going to be like Pom V alpha I, V beta I. And then you have some contribution from edges. Edge from a vertex I to a vertex J. This is going to be Pom V alpha I, V beta J. Right, so you have some X operator like this. And at some point inside the vertex operation, you're going to take the Euler class of this. Right? So imagine what happens when you take the Euler class of this. Thing. So Euler class of this is all positive, it has poles. This will fit in this will give you non-trivial denominators. And so what's this variable Z? That's Z. Sorry. Here with weight 1. No, this comes from this master space construction. If you want to interpret it geometrically, but here I mean you could add some extra equity.
If your ship is a sum of two, then it has extra scale.
That's right.
You can scale just the first term.
That's
And that's the
That's correct. So take the Euler class of this. This will be numerator, which you don't care about, has no poles. And this piece will give you. And what will these denominators look like? It'll roughly be some denominator, which roughly looks like 1 minus Z times whatever equivariant weights you have in here. Right? I mean, here,
it's not the analytical concept. In every box there's like a concept. You take the ratio.
Right, exactly. Yeah. So these are universal bundles. There will be some sum of your Kähler variables, right? But these edges carry some non-trivial weights. Some Horace T acting on these edges. Okay. And so what you're going to get here is is really as Andre says, you'll get some kind of some monomials which involve maybe some size, weights of the edge, right? These themselves. Then for each monomial in this times, you got some product of some Kähler variables, maybe S over S prime or something. So this is where those
C star Z, how did they act on the
C star scales this bundle. It scales everything of class alpha with weight 1. And it's exactly like Andrew said earlier. You have some large space of things of class alpha plus beta. In that large space, there's some special locus where your thing of class alpha plus beta really split. Yeah. No. There's no normal bundle.
No, it's right. So the P is the position of the object. Guy talks to the beta guy with some strings with mass T, and then these guys also have like lots of pieces, and those are the masses S over S prime, and the pieces of the individual constituents of the copies of the alpha guy.
Based on my based on my understanding of what's in your papers, yes.
You know, the box of the partitions and like instance on counter are just these zero brains. So that this is saying you can have the string pair of these zero brains talk to each other.
And who is Z now?
Who is Z? Z.
Say it again.
Okay, so when you do like, you know, solve theory, and you write the partition, each box in the partition is zero.
Really?
And so this, for example, is when you have like two boxes whose contents are talking to each other over there.
Doesn't matter whether.
And then, well, that's how you can conjecture.
All of it, I got the quantum. So it doesn't-
Yeah, quantum mechanics. Yeah, so Z,
No, not the big Z.
the big Z is, it's a story which comes in kind of independently. So of fundamental class of the case that we're interested in. Right? So usually inside enumerative geometry, things if you want to do integral, you want to integrate over the virtual. And so my whole walk was what integrals, but more fundamentally what these virtual classes is like a stronger kind of walk. And so the capital Z for me is my K-homology version of these things. Yeah. And so if I want to ask the question, how do my invariants change as I vary stability conditions? It's more fundamental to ask the question, how does this class change as I vary stability conditions? Right. That's my K-homology thing. Yeah. So I have some object Z, capital Z, which lives inside my K-homology group, and it's really supposed to be an analog of this thing. So the Z for me is, to be more precise, it's some functional which eats the sheaf, pairs it with one of these things, and then pushes to a point.
Yeah, it's like the instanton function of the map.
I thought when people say instanton partition function, it's kind of like a partition function with all possible insertions.
Oh, right, but yeah, I mean, you can.
Yeah. But that's an important distinction, right?
So you have something in the integral. You're not integrating.
I have an arbitrary thing in here. It's like the functional which eats what you tell me to integrate and spits out the partition function.
So you're saying you can consider like at some point. You can consider deforming the action by all possible operators. You get some function of infinite many variables. You're saying it would be the terms in the series.
It'll be the whole series.
Okay.
Yeah, that's correct. Yeah, so it's really like some kind of
More like the choice of integration procedure. So the element there is more like, like some kind of definition of your path function. It could be different.
Wait,
Like a definition of the measure in the path integration.
Yeah, exactly. That's okay. Yeah,
I was not the thing to integrate. The actual function.
Yeah, I know. Yeah, the virtual. Yeah. This is what Matt. We imagine. This is what the path integral would localize in virtual class.
Hello?
Yeah, I think maybe you two are saying something slightly different. You're saying something about the path integral itself, right?
People write path integral. It's usually there's some kind of insertion, but they're not particularly specific about the choice of measure. What is it?
Right.
What is the measure of the grade?
Yeah.
And can this object leave kind of?
Yeah, but I think what Spencer is saying is you take the path integral of